Hello, everyone. I'm very happy to give a talk here. My name is Lijing Shao. I'm from Kavli Institute for Astronomy and Astrophysics at Peking University. I'm very grateful to the conference organizer for inviting me to this wonderful conference. So today, I will talk about a new graviton mass from binary pulsars. So this is the two papers that I will mention in the talk. They are based on the work that I have done with these four people. Miaoxue Li is my student, and Professor Boqiang Ma, and then Norbert Wicks, and Shuangyong Zhou. Okay, let's start with the quantum gravity. So we know on one hand, in our modern physics, we have quantum field theory to describe the electromagnetic, strong, and weak interactions. So it is a very successful theory which forms the standard model for particle physics. And on the other hand, we have general relativity, Einstein's wisdom to describe gravity as the dynamics of curved space-time. But these two classes of theory, they are not compatible with each other. So this is extremely interesting for fundamental physics. So it means that one theory is wrong, or both theories are wrong. So this is a picture at a conference that Einstein is having with the other people. Maybe it's a quantum field theory conference, and the general relativity cannot find its place. Okay, a short summary. Theoretical physics is very beautiful, extremely beautiful, but it is not complete yet. So for the four fundamental forces in the nature, the gravitational force may be holding the key for a further step in theoretical physics. So let's look at the parameter space in gravity test. So this is the plot showing on the x-axis is the velocity, the typical velocity of a system. And on the y-axis is the space-time curvature. So we can see here is the cosmology, which corresponding to large scale structure and very low space curvature. And here is some gravity test that I have done in the solar system. So here the velocity is relatively small. It's 10 to minus 3, the speed of light. And here we have this corner, is a very interesting corner, especially recently. So here is the corner for binary pulsars. Binary pulsars, they are neutron stars. Neutron star, you know, is almost black holes. So on the surface of neutron star is very strong, strong space-time curvature. And here are also some binary black holes and also the supermassive black hole. So we can use different methods to probe the property of space-time in these systems. So we know from general relativity that gravity is mediated by a spin-2 metric field, G mu nu. So this is a very simple and elegant and a beautiful action for the gravitational interaction. So here is the gravity, and here is the coupling of gravity to the ordinary matters. And of course, if we expand the metric G mu nu into eta mu nu plus h mu nu, we can have the linearized version of the gravity. So here I show the action for the linearized version. But whatever we do in general relativity, we know gravitons, they are basically massless particles. So this is, they are strictly massless. So this is a very fundamental property for gravity. And in this talk, I will use binary pulsars to test this fundamental property of gravitons. Okay, so what are pulsars? Actually, pulsars, they are rotating magnetized neutron stars. So because their momentum of inertia is very large, and they basically is in a free fall state, so they have very small external torques. the rotation of pulsars, they are extremely stable. So which means they are kind of lighthouse in the sky. And a short summary for the property of pulsars. Pulsars, they are very, very precise clocks. So here I show an example for this PSR J0437, the frequency, the spin frequency. It's remarkable that we can measure the spin frequency to so many digits. So how do we measure these kind of properties from our observation? So basically, we use larger radio telescopes to record the so-called time of arrival of the pulses. So this time of arrivals, they are affected by something. So here is the most fundamental ones are the solar system dynamics and the binary motion and interstellar medium. So here we, for example, have a pulsar in a binary system, and it is radiating radio pulses. And these pulses, they traverse the interstellar medium and reaches the telescope on Earth. So the Earth itself is also revolving around the sun. So basically, we want to have a model for this kind of system. So here is the plot. This shows the world length for the two systems. So here the orange one is the sun. The blue one is the Earth or the telescope. And here we have a pulsar in a binary system. So the purple one is for pulsar and the green one is for its companion. So because the measurement is so precise, we can use these binary pulsars to measure the effect beyond the Newtonian gravity. So for example, the motion of the pulsar is not on a Newtonian orbit. We can measure its effect. And here are three examples that how we measure the effect. So here is the precession of the periostrum, and also the radiation because of the emission of gravitational waves, and so on. Okay, so these kind of measurements are very, very precise. So here I highlight some measurement. For example, the shrinkage of the orbit due to gravitational wave emission, we can measure to the precision of thousands of millimeters per day. Okay, so binary pulsars, they are very sensitive to tiny changes in orbit. So they are excellent test bed of gravity theories. So now we want to use them to test some specific massive graviton theories. So here is the most simple, the simplest theory that we have for linearized gravity. So here, the red part of this equation is basically the linearized Einstein theory. So if we wanted to add a mass term, so this kind of form is unique given the following two conditions. So the first, if we ask the wave equation to take a standard form like this. And we also ask the recovery rate of generativity if we put this mass to 0. So which means that there is no discontinuity in this theory. So binary pulsars can be used to constrain the graviton mass via bounding the gravitational back reaction introduced by this mass term. So through the calculations, Finn and Thornton show that there is extra gravitational radiation in this system, which is proportional to the square of the mass of graviton. So in our work, we use Bayesian analysis with a list of binary pulsars, try to put a combined bound on this delta parameter. So here in this table, you can show you can see the limit from observation, and we constructed a Bayesian analysis to put everything together and get a bound on the graviton mass. So this is the work mostly done by Xueli Miao. Okay, now let's turn to another theory. So this theory is called cubic Galileon. It's an important theory in cosmology. It has screening mechanisms. And here is its action. And here is the cubic Galileon term and the pi s is the scalar degree of freedom. And in this kind of theory, the Hiram et al., they have showed that in this kind of theory, there are extra radiation channels, including monopole radiation, dipole radiation, and quadrupole radiation. So here I plot the radiation as a function of the orbital period for a binary pulsar system. And again, we can use a list of binary pulsars to put a constraint on these extra channels for gravitational radiation. And this is the work that we done this year. And we used 14 binary pulsars to put a limit on the graviton mass. So the best performed binary pulsars, they are this B1913 and this JO737. And the combination of these 14 binary pulsars, they give a limit at the level of 10 to minus 28 eV. We also investigated if in the future we found a pulsar around a black hole, if it's a stellar mass black hole or it's the Sagittarius A star at the center of our galaxy. These kind of systems, they can also be used to constrain the mass of graviton. In particular, stellar mass black holes, they are very, very good to constrain the mass of graviton. So here I show a plot as a function of the orbital period for the projected bond on the graviton mass. And we can improve by a couple of order of magnitude in this plot if we found some very tight orbit. Okay, a short summary. So with our new test, we still found the graviton mass is consistent with 0. So in this sense, at this new level, Einstein is still right. And these are some radiative strong field gravity tests. They represent a test with some specific gravity theories. And these tests, they are complementary to the existing test, like the test from solar system, which use the Yukawa potential to constrain the graviton mass, and are also complementary to the test from gravitational waves, which use the dispersion relation and the propagation of graviton to put a bond. So in the future, the FAST telescope, the SK telescope, they will be able to discover pulsar black hole systems and put a new bond. Thank you very much for listening.